repeat chemistry video. I am super excited today to be able to present to you some content that's probably a little bit more new than some of the stuff that we have talked about previously. Right now we are going to start our focus on kinetics, that is how chemical reactions actually take place on a molecular level and the rates at which those chemical reactions take place. Definitely some brand new material. I'm super excited, so let's get going. So hopefully by the end of this video, you will be able to understand the basics of kinetics and reaction rates. You should be able to calculate concentrations using reaction rates. You should also be able to determine reaction rates using stoichiometric ratios. You should also be able to write out rate laws based on the stoichiometry of the chemical reaction. And then you should also be able to determine order of reactions based on rate law and concentration change. So let's talk a little bit about reaction rate, and the reaction rate just simply refers to the speed at which a reaction takes place. Now, when studying this, this type of chemistry is known as kinetics. Think about it, kinetics meaning like the movement of the molecules. So we're really studying how those molecules move, how they interact with one another, and the rate at which that takes place, because there are quite a few variables that play a role in how reaction rates take place. So what are some factors that affect the rate of a reaction? Well, a lot of these are probably common sense if you just think about it. The physical state of matter. Keep in mind that gas and liquid molecules tend to move faster and therefore would collide more frequently. Remember, when we think about reaction rates, what we really want to do is we want to focus on the collision of the molecules. That is what's going to determine if a chemical reaction takes place. Two sets of reactants collide and have enough energy in them to be able to convert them to products. Now, not all collisions will cause this to happen. They have to have a certain amount of energy in order to be able to cause the reaction to take place. That amount of energy is called the activation energy, and we'll talk about that a little bit later on. Think about reactant concentrations. The more molecules means more collisions are going to take place. If there are fewer molecules in a solution or a gas, then the collisions will occur less frequently than if the concentration is higher. Think about reaction temperature. Higher speed means that higher temperature means that the molecules are going to move at a higher speed. And if they move at a higher speed, then they're more likely to overcome the activation energy, which is required to make the chemical reaction take place. And then lastly, the presence of a catalyst. That's plays an important role in how collisions take place. Catalysts lower activation energy. They cause the orientation of molecules to be just right in order for a collision to cause a reaction to occur. So catalysts speed up chemical reactions, usually by hundreds, even thousands of times. We'll talk more about those a little bit later on. So the reaction rate itself is the change in concentration divided by the change in time. So it's pretty straightforward to calculate here. So let's say we have a concentration at 20 seconds is 0.45 moles and at 40 seconds is 0.43 moles, then what is the average rate of the reaction? Well, in order to do that, we need to know the change in concentration and how much time has elapsed. So if we think about it, our change in concentration, 0.54 minus 0.43. So we went and changed the concentration by 0.11 big M, and that occurred over 20 seconds. So do some calculations and you can determine the rate of the reaction. So the rate of this is 5.5 times 10 to the negative third molar seconds, or molar concentration per second. Okay? Again, pretty straightforward calculation there, but keep these things in mind. These will get a little bit more complex as we move on, but I do want to make sure you understand that change in concentration, or the reaction rate, is the change in concentration divided by the change in time. So that would be big M, which represents molarity per second. So reaction rates themselves don't actually stay the same throughout the course of a chemical reaction. In many instances, it's common for the reaction rates to decrease over time as the concentration of reactants decreases. Now that makes sense, right? Because if you have fewer reactants, there's going to be less collisions, and then if there are less collisions, then there's going to be less reactants being converted into products. Now, graphing the amount of concentration versus time can provide us with information to determine the instantaneous rate of change. And for those of you who study calculus, which is probably most of you, you will probably know that this is a calculus concept. You know, it's a derivative of the slope of the line to get the instantaneous rate of change. Something like that. All I remember from calculus is that the word calculus literally means little pebble. So, you know, something to inform your calculus teachers about. Now, for real basic simple reactions, if we consider them elementary reactions, which means that they're just one step, you'll understand what that means a little bit more later on. But we can use stoichiometric relationships to determine how fast reactants and products are made or used. So let's look at this example problem. If the rate of decomposition of N2O5 in the reaction in a particular instance is 4.2 times 10 to the negative 7th concentrations, units of concentration per second. What is the rate of the appearance of NO2 and O2? Well, this becomes a stoichiometry problem that we can use the molar ratios for in order to calculate. So if we have 4.2 times 10 to the negative 7th, and that is for N2O5, we can then use the mole ratio to get that to the rate of appearance of NO2. We just put a 4 there and a 2 there. Again, they're the coefficients of the balanced chemical equation. We do the same thing to determine the rate of appearance of oxygen. We would just have N2O5, so we have 2 down here and 1 up at the top. So essentially, 1 doubles and 1 is in half. So this one becomes 8.4 times 10 to the negative 7th. And this one down here at the bottom becomes 2.1 times 10 to the negative 7th. Okay? So again, just keep in mind that those mole ratios can play a really huge role. If we're looking at the rate at which something is being decomposed, we can then determine the rate at which the other ones are created based on the mole ratios of a balanced chemical equation. So let's take a look at the relative concentration and how that actually impacts the rate laws. So we'll use the formula up above. NH4 plus NO2 minus yields N2 plus 2H2O. We can determine some information about the rate laws. So let's look at the chart down below and think about what happens when we double the concentration of NH4 plus and NO2 minus. So if we double the concentration of NH4 plus, so let's look at experiment numbers 1 and 2. NH4 plus is doubled, but the concentration of NO2 minus stays the same. Take a look at the observed initial reaction rate. It doubles. Makes sense, right? If you double the concentration of one, it's going to double the concentration of the other. Let's take a look at NO2. Let's go scroll down to the bottom there with, let's look at 5 and 6, because when 5 and 6, NH4 plus stays the same, but NO2 minus is doubled. You notice that the reaction rate also doubles as well. Reaction rates are directly proportional to each other. Now, this is going to have an impact on what is known as the rate law, which governs how concentration impacts the initial rate of the reaction. Let's take a look at the next slide. So we use this information to determine the rate law, which is given as the rate, which should be the observed initial rate, equals K times the concentration of A to the M power times the concentration of B to the N power, where K is the rate constant and A and B are the concentrations of the reactants. Now, M and N are reaction order, and that's something we're going to discuss a little bit later on, because when you double the concentration, it doesn't necessarily double the reaction rate, and that's where reaction order actually comes into play. So if we know the concentrations and the rate, we can solve for K, utilizing the previous data. And then once we know K, we can calculate the rate for any particular concentration. We use an initial rate. We were able to solve, plug in rate, A and B, and then we can solve for K. And then once we know K, any concentrations, then we can determine the reaction rate based on that information. So again, up here at the top, we look at the generalized formula for the reaction rate. Now, M and N are called reaction order, and this is shown as an exponent. So the previous reaction had reaction orders of 1 for each reactant. So the reaction order itself tells you a little bit of information about what's going to happen to the reaction order when it changes the concentration. So if the reaction order is 1, then the reaction rate is going to double when the concentration doubles. When the reaction order is 1 and the concentration doubles, the rate doubles. When the concentration doubles, the rate doubles. If the reaction order is 2 and the concentration doubles, then the rate quadruples. That's super duper important. Please make sure you write that down. The overall reaction order is the sum of the orders. So the previous reaction had an overall reaction order of 2. And sometimes, but they're not always the same as the coefficient of the reactions. So let's assume that a reaction rate of K times the concentration of A times the concentration of B squared, which is the fastest reaction rate. Well, let's just plug in our numbers and solve. So for the first one here, we're going to have 5 times 5 squared. 5 squared is 25 times 5 is 125. And we'll put K in there as well because that is part of the reaction rate. So 125K. For the next one, 7. 3 squared. 3 squared is 9 times 7, 63 times the rate constant. And then 7, so we're going to have 3. 7 squared is 49. 3 times 49 is 147 K. So the fastest reaction rate is going to be the one at the bottom, where we have 3 molar concentration of A and a 7 molar concentration of B. Again, just some ways you could plug in some numbers and solve for these types of problems. So I know the top of the part is a little bit blurry, but we should be able to answer these questions pretty straightforward. Now remember, the reaction rate doubles if the order is 1, and if it quadruples, it is 2. So the first thing says, determine the rate law for this reaction. Well, when we look at the rate law, we're going to look at our 2 reactants, all right? So our rate law, we're going to start with K times the concentration of NO and the concentration of H2. Now remember, we need to solve for M and N. So let's take a look at what happens when we change the concentration of NO. Well, we're going to look at the ones here, experiment number 1. We're going to compare that with experiment number 3, because the concentration of H stays the same, but the concentration of NO doubles. So what happens to the reaction rate when the concentration of NO doubles? Well, if you look, it goes from 1.23 times 10 to the negative third to 4.92 times 10 to the negative third. So it does not double, it quadruples. So if it quadruples, then the reaction order is 2. The order there is 2. And then if we look at H, let's look at the first and second one here, because NO stays the same and H doubles. So if H doubles here, the reaction rate also doubles, so the reaction order there is 1. So we've solved for that pretty straightforward. Let's go ahead and calculate the rate constant. So in order to do this, we can just pick any of these and plug in and solve. So let's just do the first one there. So our initial rate is 1.23 times 10 to the negative third equals K times the concentration, 0.1 squared times 0.1. And now we can solve for K. It's equal to 1.23. I'm not too terribly concerned about the units at this point in time. And then the last part says to calculate the rate when you are given 2 different concentrations here. So again, we just plug back into K, and this time we're just going to solve for rate. So the rate's going to equal 1.23 times concentration of NO, 0.05. Remember, we square that, times 0.15. Again, we plug that back into our calculator and solve. What we end up getting is 4.6 times 10 to the negative fourth. Remember, that is rate, so use your proper units there. Okay, and like I said, it's pretty straightforward, so just make sure you know how to calculate those, plug those in, be able to determine the rate law, all that good stuff. Now, another aspect when we go through and evaluate these types of problems is to look at them on a graph. And the key thing here is to look at them when they are linear, because that is going to have an impact on the slope and also has an impact on the reaction rate. So if we have a first order reaction, that is the total reaction is first order, the rate depends on the concentration of a single reactant raised to the first power. So the differential rate law is the natural log of the concentration of A at a certain time equals negative K times T plus the natural log of the concentration of A at 0, or at the initial rate. Now, when this graph, this causes the slope of the line to be linear. Notice the negative slope. The key thing here, and to notice this when it is in a graph, is that you're looking at the natural log. So when you see natural log in a graph, you know that it is a first order reaction. A second order reaction is one whose rate depends on either on a reactant concentration raised to the second power or on the concentrations of 2 reactants each raised to the first power. Remember that the total reaction order is additive. The differential rate law is 1 over the concentration, and notice that it has a positive slope. So again, keep these things in mind. We want to make sure that the line that we're looking at is linear. And in order to do that, we either need to take the natural log if it is first order, or take 1 over the concentration if it is a second order reaction. Note the positive slope as well. And then lastly, a zero order reaction is one where the rate of disappearance is unrelated to concentration. We don't see this very often, but in this case there is no natural log, there is no 1 over the concentration, but notice the negative slope as well. So you do need to keep in mind the difference between zero order, first order, second order, especially when they look at it in a graph. You want to look for which graph provides you with a linear expression of the differential rate law, and then look at the x-axis. Look at the y-axis and look and see if it's just the concentration, if it's the natural log of the concentration, or 1 over the concentration. That's going to play a huge role in determining what order the reaction is. So another example of this would be half-life. And if you remember half-life, you could think nuclear chemistry. Well, that is a first-order process. So that's given by the formula T to the 1/2, meaning that the half-life is 0.693 divided by K, which is the rate constant. Okay, so there are some ways you can go through and calculate these things, but half-life is a pretty straightforward calculation. Also notice the graph. The graph is in a kind of like a parabola almost. It's a curved line. It's not linear. If we were to take the y-axis and do the natural log of this, then you would get a straight line because half-life is based on a natural log scale. And then also think about temperature and the rate as well. The collision model helps us understand how and why different reaction rates occur. So think about temperature, orientation, and the concentration impacted the model down below. Effective collisions are very important, and so the orientation of the molecule and the speed at which it takes place is very, very, very important. So, like I said, just kind of keep those things in mind. It goes back to what we've talked about previously, but it's a pretty straightforward concept. You just need to make sure that you're thinking about it a little bit on a deeper level. So again, lots of different practice problems that are associated with that video. Hopefully you've met the learning objectives for today. Make sure that you can understand the basics of kinetics and reaction rates, calculate concentrations using those reaction rates, and determining the reaction rates using stoichiometric ratios. You should be able to write out rate laws and determine the order of reactions based on the rate law and concentration change. Again, lots of information for today, but hopefully you guys got most of it. We will talk about it next time when I see you in class. This is Jayland Bio. Make sure you like, subscribe, leave a comment down below, and make sure that you shop merch. We will talk to you guys later. Have a great day. Bye-bye.